will continue with the ground formation types today. Basically, cohesionless, cohesive. I think that's what I used to classify. But then sometimes you also have very strong ground formation like rocks, but very rarely used for pile foundation types. Very rarely means sometimes we do encounter such type of formation wherein you might go for pile foundation, but very rarely, because once you identify this kind of rocky formation, we will try to avoid pile foundation in these locations. But in any case, you identified a better formation, and in some locations within the group, sometimes you get a boulder, big boulder, like the one example I was talking about in the previous class. Among the 4 piles of a jacket, 1 pile may not be able to drive just because there is a localized rocky formation. So, what else can be done in order to get the sufficient penetration to get the the foundation depth? So, we may also look at rock as a material for pile load transfer, which is slightly different from the other cohesionless or cohesive type of soils. So, you can see here cohesionless soil is primarily a particle of not having any cohesive the characteristics between the particle to particle, whereas the cohesive soil is basically a fine particles of bonded together, which will have a slightly better bonding characteristics. So, you see here with these two we can actually find out what could be the difference in behavior when you apply loading. So, that is the idea behind trying to find out the characteristics or the properties under loading, and by doing this kind of segregation you need to develop, or in fact we need to understand their behavior and then characterize them such that in future foundation design you can use that basically the properties. So, over a period of time, for the last 100 years, many devices, many ideas have been devised to identify strength characteristics of cohesive soils and the cohesionless soils, which we will be using them sometimes empirical, sometimes based on experiments. So, you will have to be very careful in assessing the characteristic, because most of them is not easy to derive from first principle of physics. So, that is why soil mechanics become little bit of troublesome in terms of mechanics compared to structural mechanics. What you normally learn is very straightforward. You do not need to remember anything, you can derive every one of them, the characteristics of deformation of structures very easily, whereas here many of them the principles are behind how the materials are arranged together. Rocky formation basically is quite strong in nature. So, one of the difficulty in rocky formation is how you can install the foundation, whether it is a shallow foundation or a pile foundation, because it has got enormous strength against compression, and of course, you need to make sure that you reach that. Every time when you design a foundation, we want to take it to this place, but then taking it to that particular rocky formation or a hard strata itself is a big challenge. Among the different types of rocks, we got varieties of classification like sedimentary rocks, granite, blue granite, you will see sandstone, limestone, slightly reduced characteristics, which are different formation types. I think if you are looking at the geological process of formation of these types of rocks, you will be able to understand, which I think we will leave it here. So, among the cohesive soil and cohesionless soil, you can see sand, gravel and slightly bigger particles. The cohesive soils are fine particles of different sizes, ranging from microns to a few millimeters. So, you can see in I think one of the slide I have given the sizes of the ranges. So, you can see the particle shapes, because these are formed by nature. So, you can't have a predetermined size and predetermined shape. So, you can have many types depending on the type of weathering. I think we were looking at in the previous class, depending on the type of weathering and the mixture of weathering cases, you may find different shapes and sizes, just an enlarged photograph of particle sizes. So, mostly the clay type of structures or the clay type of particles will have a flat base. You will see that it is elongated. I think you will see in the next picture something like this. Most of the clay particles, if you go into a microscope, you will see that it is elongated. It is not going to be something similar that you see here in this type of particle. That is why this is a magnified picture, which is easily seen that the sheets of particles are arranged together, which makes basically the basic characteristics of fine particles. One of the important property that we can easily and physically understand is the particles when you arrange in nature without any influence of external forces, how they get organized themselves. For example, you take a case of dry particles of sand, gravel or any material. In fact, you can take any natural material of grain sizing, different sizes, just pour them or just drop them from a slight height, which will arrange themselves and slide. So, you can see, you see the shape of this particular fine grind gravel, it is not very big ones, probably 20 mm, 30 mm. So, you can see it takes the shape of a particular angle. Now, you can realize you take a water and just pour, what will happen? It will just go flat. So, that is exactly the two extremities. So, if you take a rock, solid rock and just cut into two pieces, you can see the vertical face, is not it? It does not go, it is not going to slide down, and basically that rock has got intergranular bonding and it is not allowing the particles to drop. Whereas, if you take a sand or a gravel, it does not have a bond, but it has got only a frictional resistance against sliding. So, it forms certain angle. So, water and rock, and in between you got the particles of different size, different grouping. So, if you have a very equal sized particles of same in that group, it will form certain angle. If you have a mixed particles of different sizes, you know, it goes in between the space between the bigger particles, then you get a slightly different angle, because it gets packed well and probably will not allow sliding that easily. So, you can see of granular particles of different size will have different angle of sliding resistance, which we call them angle of repose or natural behavior of the material against, you know, sliding and failure. Now, if you add water, what will happen? Slightly, not too much, because submerged versus the partially saturated, you may actually create a slight bonding. So, that is why the wet sand might actually stand slightly bigger angle than dry sand. So, you can see this is what we wanted to see. If you actually look at the natural when you are excavating trench, for example, for your shallow foundation, I think most of the small buildings you do the trench. So, you go and cut. Normally, we do not want to cut a bigger one, because it is more effort is required. So, you just do a vertical cut. If the soil particles are slightly saturated, not fully saturated, you will be able to actually make a vertical cut and the particles will not slide down. But if it is a dry sand, you will never be able to make a vertical cut, it will keep on sliding. So, that is the idea behind how the soil behaves depending on the moisture content, depending on the particle sizing. At the same time, if you have a clay, for example, very soft clay, you go to some places in the east coast, I think marshy area, you go and step on that type of area, what will happen? Your leg will easily penetrate and it will just go down. Such type of clay, if you try to pour like this, it will almost go very flat, probably will not even form a angle. So, you can see this is one of the very simplest idea of the strength of soil can be understood, and this is one of the parameter, you know, the past researchers have come up with a measuring device or a measuring parameter, which can be used to relate how strong against failure in terms of frictional resistance, and that is why we want to use this parameter predominantly for the particles of some size. We call it coarse grained soil or cohesion less soil, basically because it does not have any cohesion, primarily friction. So, this angle of repose is a measure of how the soil is going to behave when you leave it to disperse itself. As I mentioned here, 0 to 90 degree normally is two extreme cases, because it is solid rock versus water, but typical range is somewhere between 10 degrees to 40 degrees, something like this for most of the soils. Now, if you have a very good dense sand, you may get 40 degrees, loose sand you may get 10 degrees, 15 degrees, 30 degrees. So, this is one of the parameters very easy to measure, is not it, because if you just do this natural exercise, you can get it. Of course, in terms of actual soil, we do not do this, we actually come up with several methods of characterization and empirical methods of relationship between angle of repose to what was measured at site, you know. So, that will be empirical. Of course, if you have a very good sand, you can do that in laboratory as well in the site. some typical examples of the values, you could just read it. What is of our interest is basically the sand, somewhere very good sand 30 degrees, 34 degrees, 35 degrees is a kind of measure that you will normally get for most of the foundation sand available. Of course, you could see the comparison is a wide variety of numbers that exist for various granular materials. Clay particles. So, what we have done is we have just characterized one parameter, one single parameter that gives us an idea that how the sand will behave depending on the basically the sizing, particle size, how well they are packed, we are going to see that one slightly later, and how big is the size, whether water is present or not present. So, with that we can find out what kind of angle that from this angle. Now, we need to relate that to strength against failure. So, that will be done slightly later. Now, let us jump on to the clay structures or clay particles and the shape and the arrangement and how they are behaving when you apply loading with and without water content. So, basically that we can see just. So, you see here various pictures, what you can see here, the first one is almost flat, every one of them is just organized. It is not that we are picking one particle by one and then arranging like this, it is naturally formed, somehow over a period of time it has rearranged itself due to various changes happening during the process of formation and existence. So, you can see here is a fully dispersed. When you try to apply loading, it may actually not change form or shape too much, whereas if you look at this book house type, basically in a zigzag manner organized in such a way that it is having larger voids between interparticles. So, when you try to apply loading, what will happen? It will get dispersed. So, you will see a larger deformation. So, you could see the particle arrangement itself is going to give the behavior different, and that is going to be a bigger worry, because for some type of clay you will look very nice, but then when you actually apply loading it will disperse laterally or get compressed in this fashion. So, what we need to do is we need to look at what is the formation types and the history where it was located. Depending on that, you could actually assess whether the clay structure is going to be this type of pattern or is this type of pattern, because very difficult to get the undisturbed sample if the soil is loose. And you may also have many times not pure clay, except in some cases like coastal areas, river beds, you may get reasonable uniform clay, but in the natural deposits over a longer period of time you may actually have mixed particle sizing, clay particles as well as grain sized sand particles, or sometimes big boulders like what you see here. I think this is supposed to be gravel. So, you could see mixed particles, which makes us little difficult to get the characterization, because when you have all three of them together, then which methodology will be used, because we were just looking at grain sized particles, which is of sand, clay particles, you may just get some property for this, but if they are mixed, then we need to generalize the whole method and try and figure out what can be used. Now, to understand physically, to be a better geotechnical engineer, you just cannot just sit in the home or in the office and just try to design and understand the behavior of the soil. You need to go very close. So, what you need to really do is every time when you actually want to construct a foundation or do a borehole investigation, you need to feel it. You take the soil, visually inspect. You could see from the visual inspection itself, if you are an expert, can actually identify without doing any test the type of soil at least, because from the color, from the texture, from the material mixture, you could say this is a sandy clay, predominantly sand or predominantly clay. You can find out from the picture or from the material color itself. So, that is why every time when you do borehole, you have to go and feel the soil, how it can actually behave. For example, you take a lump of soil, you try to compress by hand, you can see whether it is brittle or it is having large watt content or the particle sizes, or you just compress between your fingers, you can see whether it is plastically deforming. So, all these characteristics, of course, you can do it in the laboratory, but then the first hand information that you feel and you get it from the site itself without disturbing the soil, the samples could easily understand, so that you can write and classify. Because the reason why we need to do this, many times we use empirical formulas in foundation design. So, once you classify to a particular character size, then you can later look for historical information on such type of material, where others have done testing. You are not able to do testing, but of course, you have realized the material is this color, this texture, this mixture, and then the characteristics of what you feel at the site. Then you can later go and look at your historical data and basically try to assess the strength characteristics from there. So, that is why the first information report that you arrive or get from the field investigation site is very important. That is why the field log is reasonably important, more than what you actually do in the laboratory, because after all laboratory you are bringing a sample, you do not know how much of disturbance has been done or may not be able to get an undisturbed sample, and then you do a testing in a small scale. The behavior could be different than actual field behavior. So, you need to be assessing the site. Some of the ideas given by past experts, I would say, over a period of several decades, that this soil behaves this way. So, that is what is summarized here. I think it is very easy. So, if you look at one of the important idea, that if it is a sandy soil, for example gravel or coarse grained material, the best way is to try to penetrate something. So, what these guys have done, penetrate a 50 mm wooden peg, just take one and then just try. So, if it is solid rock, what will happen? Just big boulders, it will not go through, isn't it? If it is a fine sized particle of sand, loose, so you are able to penetrate. So, that gives you an idea that what kind of, whether dense material or loose material. If you have various sizes of sand, for example 1 mm, 3 mm and mixed together, which has got voids less than, if you have only bigger particles, when you try to penetrate something is very hard to go. So, these are some of the ideas that you get, very important, because that gives you a feel of the soil, how they are stronger. Similarly, silt, loose or firm, clay. The difference between silt, clay and peat is only particle sizing and the nature of particles. This organic, this is inorganic, of course, and then you have a lower size particle is silt, slightly higher size particle is clay. So, that is the major idea, otherwise the behavior is going to be almost similar. So, clay, if you take molded by a light finger pressure, just basically you are able to just press, it gets different shape. Plastic clay, basically once it is deformed, it is not going to come back. So, you can see here soft, stiff, very stiff, all of them the characteristics by which you can feel the soil. With different moisture content, the clay and the silt is going to behave differently. If you have too much of water content, what will happen? You just take it, it will just get flat. If it is less water content, it will just crumble, it will just become independent lumps. I think you can try at home, or outside. You take a small clay particle or clay lump with a very small content of water, when you just try to press or compress, they will break easily. But if you have sufficient enough water, whatever you do, it will become thin, but it will not break that easily. So, you can see that characteristics gives you an idea, water content make the behavior of the soil different at different percentage. So, that is the idea, the devices that is very similar to the idea that we have got for material like steel. We just try to feel that how the material will behave under tension loading, and you characterize tensile test using strain versus stress. It is very similar, only thing is it is slightly complicated, because this material do not have inter-particle bonding. They are individual particles, they are not connected to each other, unlike the steel or other materials. So, that is where we cannot apply the same principle to this material. We have to find a material which is suitable to be identifying strength. All of you understand, is a slight different technique. So, similarly, the characteristics also can be identified with respect to whether it is homogeneous. By look itself, you can see whether it is very uniform, have no cracks, interparticle cracks or surfacial cracks. So, you can see here homogeneous or interstratified, homogeneous weathered. If you look at a rock, you can see cracks all over. So, you can identify, because these are the characteristics will help in assessing the basically the strength characteristics in future, because sometimes several times the samples that you bring from site, if you are unable to do testing, you are helpless. So, identify this and then later relate this to existing literature. Similarly, clays, fissured clays, intact clays. Intact clays will be like a very fine molded material. When you cut across, you will see no voids or cracks. Whereas, if you see here some of the dried clay, for example, in a partly dry area where water was there, if you go to a water body in villages or even in outskirts of Chennai, during summer, if you go enter into a lake, you will see the clays just broken, and if you just take one particle and just open it up, you will be able to see these fissured clays, because the water content is getting dried up. So, you can see variety of ideas to identify how the soil will behave at that type of additional properties. So, these are required, and these are not going to be coming out of any of your testing. When you do a laboratory testing, you will not be able to tell, that results of the test will not tell whether it is a fissured clay or intact clay. This has to be coming from the first report or the first log the people prepare at site, because they should be able to identify whether this type of clay or that type of clay or the material is homogeneous. So, this has to be identified and written even before you do the laboratory testing. So, the idea behind, I think, because of the empirical in nature, the relationship between the material and the characteristics. Now, what are the properties that we require for us to basically assist in classifying the soil? The first one, I think by this time you should have understood coarse grained versus fine grained versus the big lumps. Big lumps is your rocks, which I think does not require sizing, it can be small, it can be big space. Whereas, fine grained versus coarse grained, the first one what we require is the particle sizes, of course, shape, and then basically the distribution of the particles within the given soil mass. For example, you take every one of the particle is 1 mm, is well uniform, that means. So, it is one type of characteristics, or you have a soil particles of 1 mm, 2 mm, 3 mm, 5 mm within that soil mass of certain percentages is going to behave slightly different. So, that what we need is particle size and also the distribution of particle size within the given soil mass also needs to be. So, how do we do it? It is very simple exercise of sieve analysis, which I think is very familiar. I think some of you might have already done. So, that particle size distribution will tell us how it is going to be whether it is a clay type of material or it is a sand type of material or mixture of them. Sometimes you will have many occasions in marine deposits, you will find basically the starting layer may be pure clay, followed by sand, followed by sandy clay or clayey sand. Now, you see here there are two distinctive names I was just trying to give, clayey sand or sandy clay. So, you need to see the percentages by which you can say whether it is a sandy clay or clayey sand. So, typically the mixtures needs to be identified which is a predominant material. For example, if you have more than 50% of sand, then it is actually a sand, but with a little bit of clay. So, clayey sand. So, you can just see the idea behind is, as I mentioned, we are just trying to classify based on this. So, particle size distribution is easy to determine, which I think some of you might have done already in your civil soil mechanics lab. Atterberg limits is nothing but the water content, which just I was explaining. Even if it is sand, water content makes them behavior slightly different. So, what we need to find how much water is present in the particular soil, how they are going to behave, liquid limit, plastic limit, we will see later, and then the plasticity index. Then the density, as you can see, loose versus dense. We were seeing the sand material, if it is loosely packed natural form, when you just poke, it goes very easy, but if you have shaken the sand or soil and made them to get well packed, even if it is clay, in fact, if you look at a clay material, if it was a book house form and you try to apply loading and then deformed, next time when you come and apply the loading, it is not going to deform that much. So, if it is prehistorically have been compressed from the book form to a form where the compression is going to be very less. So, the reorganized layer is going to take higher load than the younger clay. We call it younger clay or older clay, basically the clay depositions. So, you could see that the density is also playing a major role. So, as long as you know the density of the material, you know very well how much load it can take, because it is well packed, very dense. For example, you take a rock, is fully packed, intact rock or porous rock. If you look at a porous rock, it can actually reorganize under certain loading. So, basically get compressed because voids is present. So, that is why the predominantly and easy to do density of material is easy to do, because you do not need a very scientific idea. So, what you need is the weighing. Then goes to the strength parameters, as we mentioned, angle of internal friction, angle of repose, which is what we were talking about for sandy type of material, which is definitely possible to get. So, for coarse grained material, we will definitely use angle of internal friction, angle of repose. Shear strength, because as you know very well, the clay does not have angle of repose, because when you just have spread, it will just not be able to measure because of water content. And remember, all our marine conditions, we have a fully saturated soil, that means we are always under water, whereas in onshore you may have dry soil, you may have partly saturated soil, because after rain water percolates through the soil, and over a period of time the water evaporates or settles down. So, leaving behind partly saturated void space within the voids of the soil particles, some amount of water, some amount of air, and remainder is, whereas in marine conditions you are always going to have fully filled with water, wherever the voids is there, it is always filled with. So, we have a submerged conditions, fully saturated, compared to the onshore conditions of either dry or partly saturated with water. So, what we need to see is how do we establish, you take a soil, if it is a fine grained soil, when you try to separate the particles away somehow, how they will break, the shear strength. So, basically as you know very well, if you try to pull them apart, they are not actually going to take any loading, because soil particles are individual, whether it is clay or sand. So, what we need to see is what it has got under shear strength. So, basically the shear strength has to be established by several means, lot of methods are available, we will see one by one later on, both in terms of you can do it in laboratory or you can do it in field itself without taking samples, and corresponding elastic properties, basically the Poisson's ratio. Hope all of you understand what is Poisson's ratio, and the modulus of elasticity, very similar to steel material. So, this modulus of elasticity is very important, because the deformation characteristics can be determined if you know what modulus of elasticity. Of course, when we move away slightly, we might change from modulus of elasticity to some other parameters during our course of this particular title for vertical deformation, horizontal deformation. So, these are some of the parameters have been identified to be useful in terms of strength characteristics of soil and relating the strength characteristics to the foundation capacity. So, we will see one by one. Particle sizing, as I mentioned earlier, you see the clay type of particles less than 0.02 and silt between 0.02 to 0.6, and then sand between 0.6 to 2 mm typical sizes. If you look at some of the codes, some numbers could be slightly different, but does not matter, that is the kind of approximate numbers. So, you could see the sand is between less than a millimeter to 2 millimeter. So, if you just pick up a sand, you can see 2 millimeter is quite visible size, you are able to identify the particles even by the feel of the fingers, you can take it and take one particle separately. Whereas, when you are looking at less than 0.02, it is very hard to find individual particle, they are so small, micron size, and they will be, if you pick up, you will pick up few of them together. So, that will give you a feel that whether it is actually clay or sand. and gravel, not to say, is quite a big boulders. Normally we use gravel for many construction activities in concrete, is not it. So, but that varies from anything beyond 2 mm to 60 mm or even slightly higher, does not matter. Boulders, we call it more than 60 mm, we call it big boulders. Sometimes they do exist in case of some soil layers, where you will find big boulders and then gravel and basically sand. Whenever the boulders are existing, pile driving is potentially dangerous. You will see later on, though we can break, while the process of breaking that boulders, the pile will actually fail. So, that is one of the danger, where many places, especially the deeper foundations like pile foundation fail terribly, because the presence of boulders which cannot be identified even if you do many boreholes, because boulders of say 1 meter size, you cannot identify if you do 4 boreholes or 8 boreholes, because it can be anywhere, it is very difficult to find out. So, this sieve analysis, how do we do it? We take a soil mass. I think if you have not seen, we will go to one of the days civil engineering laboratory and see this. Is very easy to do. So, you need to just dry the soil and then use sieve of variety of sizes. Of course, you can follow IS sieves or British code sieves, almost similar size, I think, if I am not wrong. So, you have a different mesh and just pass through each one of them and identify how many percentage of soil by weight passes through each of the sieve. You take one lump of soil mass, 1 kg, 2 kg, 5 kg, as much as you want, and just pass through. So, if you take the finest sieve, for example 63 microns, so you just use that, how much soil goes through. If nothing goes through, all of them are bigger, 100% bigger, is not it. So, every time you change the sieve size, you will be able to find out how much percentage of soil passes through that particular sieve size. So, if you take 62 mm as a first one, put everything goes down, because all the soil particles are smaller than 62 mm. I think it is very easy test, which gives you an idea, and then like that if you do it, you will be able to get percentages of soil particles passes through a particular sieve size, is called, sometimes we denote by D size, D10, D30 and all that, we will see later. So, this sieve analysis is the first part of any soil laboratory testing, that will give you an idea, range of particles present in the soil mass. So, typically if you look at the graph, particle size versus percent finer, if you just have a line across spread over all sizes, is very good, because then soils is having every particle size from micron size all the way to say in this particular case 5 mm, and every one of them have certain percentages. So, it is just mixed. This will be a good soil, because all the voids is filled with the finer particles. So, how do we define? So, effective size, of course, is not used for foundation design. Several times we use it for the hydraulic flow through soil material, especially the dam construction. I think you might have studied if you have gone through a dam engineering. So, this effective size, we call it D10, is the parameter in the diameter, basically the size, the corresponding to 10% finer, that means the material size that has diameter less than this D10. So, basically D10 is a size, 10% is passing through, remainder is not passing through. So, basically 10% of the material is finer than this size. So, that is D10 can give you an idea of how the flow or the drainage is possible. If too much of fine particles, drainage is not feasible, is not it. If it is having too small size, it is not good. Similarly, the uniformity coefficient is devised to identify whether the number is too big or too small. If the range is larger, for example, I have got smaller size and as well the larger size, then it is a larger uniformity coefficient. So, you can see from this picture is basically, you see here the size for the C type of soil is having fine soil from a smaller particle all the way up to 62 mm cut across all the sizes. So, you can see for C type of soil, the uniformity coefficient is very large, because it is the ratio between D60 to D10. So, D60 is one extreme, D10 is the other extreme. So, when you do that, you get a bigger number. So, basically that is the idea behind people come up with this type of basically some notation to identify these numbers will give you a feel whether the soil is having larger spread, smaller spread or no spread. For example, you take only one particular size, all of them are 2 mm, very good sand like grain sand, then you will have one vertical line, isn't it, all 100% only one size. So, such type of characteristics is very easy to identify. Similarly, coefficient of gradation is another characteristics using D60, D30 and D10, each one you get from your sieve analysis. Some pictures to give you the grading, we call it grading, is for example, if you take this one, the lower one is well graded, having presence of all types of particles from 0 to, that means clay all the way up to several, each one of them having certain percentages. Whereas, if you look at the poorly graded, it has got little, then it climbs up vertically, that means one particular size is having larger percentage, isn't it, and then some smaller percentages of maybe fine particle, some smaller percentages of the bigger particle, but predominantly one particle size. Gap graded, you see a flat line, some portions do not have or some particle sizing is missing. For example, you may have 0 to and then in between there is no particles of that size, then suddenly you have different particle size, which we call it gap graded. That means there is a missing particles in that whole lump of soil. So, you have well graded, poorly graded or gap graded. This gives you an idea why do we need to this, is basically to find out whether the soil mass has got more white space or less white space. Why? Because the more the white space, when you apply loading later, what is going to happen? The particles are going to get reorganized because of the arrangement and gets deformation, that means larger displacement, not good for us. So, that is why if you are able to assess the characteristics of presence of type of particle sizing and voids, and in fact added together, if you can find out whether it is a organic or inorganic, because that material itself will behave differently, and you can find out whether the soil is good soil or bad soil, because many times you want to make a decision whether we should put what type of foundation here. So, that is why this grading gives you an idea that the soil is going to behave, how much deformation is going to take place. The next one is a similar graph, only just slightly just to get a feel for numbers, what kind of ranges of values you are looking at, especially the Cu and Cc. So, Cu larger is good somewhere here. Similarly, Cc is less, is basically for the soils having a larger spread, that is exactly. If you look at the soil B is just nearly 1, because it is just vertical line of a particular soil particle presence. So, all these properties you should know how to calculate given this. In fact, if you study soil mechanics, this will be one of the areas where you will be given the particle sizes and you will have to calculate these parameters and classify the soil yourself. Whereas, I think this is not a basic soil mechanics course, so we will not go into that, but you should know if you are given a soil particle sizing percentages, you should be able to classify soil as well graded or gap graded or poorly graded, which gives you an idea that you can apply this principle, because later when you are going to look at empirical charts or look at some relationship, you will be looking at well graded sand. Then you go to the table, you can pick up the parameters that you need to choose for design purposes. So, that is why we need to know this classification. The same information written in a tabular form. So, just for your information.